Hello, welcome everyone to the ecosystem track. I'm happy to have Twistlock here today to do their session on stronger security through containers and machine learning. And I have John Morello here from Twistlock who will get started. John, off to you.
Thank you, Tricia. As Tricia said, I'm John Morello. I'm the CTO for Twistlock. How many of you guys have heard of Twistlock before? Just a general show of hands. All right, so just a very quick overview. So we've been around for about 2.5 years now. We were originally founded and focused from the very beginning on helping customers secure their containers and microservices. So we have a lot of different capabilities in our product, from vulnerability management to access control. We actually help build the authorization framework that ships in Docker. We've done a lot of work recently around making Swarm, Secrets Manager pluggable in Docker. So a lot of stuff in the open source. And we obviously also have our commercial product that we sell that does a lot of capabilities, vulnerability management, compliance, and runtime. But today we're going to talk a little bit at a high level about not Twistlock specifically, but about the way that containers work and sort of the fundamental characteristics of containers that enable an industry opportunity, I would say, for us all to do security in a smarter, more autonomous, and just frankly more scalable and effective way than you've been able to do in the past. And so I'll be happy to answer questions as we go through it. The session's only 20 minutes, so we probably don't have a chance for a lot of them, but if you have some questions as we go through, by all means raise your hands and I'll be happy to answer them. You know, I don't think this is of a surprise to anybody that's in here, so I won't belabor the point, but, you know, obviously people continue to use containers more and more. The reason I have this slide in here, though, is while it's obvious, I think, to all of you guys that are at Dockercon that people are using containers more and more, from a security standpoint, the effect of this trend is a little bit different. And the effect of this trend is that you now have more and more organizations and more individuals using containers that don't have necessarily the technical depth that the early adopters do. And because of that, you end up having a lot of situations in which people may not be doing the right things or the smart things to secure those environments, or even to secure the applications that they run inside of those containers. It's not really about talking about the security of containers. We're not going to be having some debate about are containers secure. Hopefully all that's pretty settled science at this point. But the idea really is, as you put your applications in containers, are you doing the things that you need to actually secure and protect the containers and the contents of those containers and the microservices that run in there? And what are containers enabling you to do that you haven't really been able to do in the past? If you think about the traditional approach to security, security has been historically very focused on a lot of manual effort and a lot of what you might consider to be blacklists or block lists or something like that. In the sense that, think about your traditional like firewall rules or your anti-malware system that might be on your PC or something like that. It's typically configured with a set of signatures of some kind or indicators of some kind that say, here's all the things that are possibly bad in your environment, right? Here's all the signatures of things that are malicious and, you know, IP addresses that are quote unquote evil and things of that nature, right? However, that model doesn't really scale very well when you think about that, you know, containers are designed to be very frictionless as you move from development to test to production and so forth. They're designed to be a lot more scalable. You're going to have lots more containers than you have like traditional entities. And so when you think about those traditional tools that are focused on those block list approaches and those signature-based approaches, not only do they not really work well for containers, but I would just say in general, if you're a security pro, you probably would sit back and say those tools just don't work well, period, today. Like the approaches that we've had to security as an industry historically have not really kept up with the kinds of threats that exist right now. And the reason for that is the actual security mechanisms that were used were very separate from the actual applications and the data that those applications have that you're trying to protect. So if you think about like the old world model of security, this is a little bit facetious, but it's not entirely inaccurate either. I'm sure you've probably seen this before. Your developer is going to sit down, like if you really have a very security-focused organization, and most organizations are frankly not very security-focused, but if you have someone that really is, you know, your development team might sit down with your security team and say, hey, my application behaves in this way. You know, it runs WordPress on Apache in this particular version, and it listens on this port, and, you know, and here's the signatures of everything and so forth. And if your security team is like really on the ball, they're going to go to a firewall and they're going to configure some rules there. They're going to go to an IDS. They're going to set up some rules there. You know, maybe they have some sort of anti-malware tool. They'll set up separate rules there and so forth. And then the very first time that application changes, you know, and it listens on a different port, it runs a different process, or just a different checksum of the binary that you have in there, now those rules have to be changed, right? They have to be updated. And no one keeps up with that stuff. And so what do you really end up with in most cases is that allow all sort of rule, right? People fall back to the perimeterized approach to security where they're saying, I know my application security kind of sucks, but I have a firewall out there, right? So the firewall is what makes me secure, which I think all of us can realize is sort of ridiculous, but it's actually the default operating posture of a lot of organizations today because they just can't keep up with the amount of change that the applications require to keep that in sync with what they need from a security standpoint. So the philosophy that we have with it is basically like either you can have DevOps and containers and all the benefits that brings in terms of being able to rapidly iterate your application and deploy it more quickly, change it, really like software enable your business, as everybody likes to talk about. Or you can keep your old world security approach where things are very manual and very static in nature, but you can't have both. You really have to figure out, do I really care about DevOps? Do I want to embrace that? Do I want to take advantage of all these capabilities that containers provide to me? Or do I want to stay with this old world security model? Because the two are fundamentally incompatible. You have to have a different approach to doing security if you want to actually be able to take advantage of DevOps and have the security requirements that you need. So what are those differences? What's special about containers that kind of changes and forces you to have a different security model for it? There's really kind of four things that we think about and really kind of influence the way that we built Twistlock, but also just are in general things that force any security organization, any security vendor to change their approach when they start thinking about containers and microservices. First of all, you typically have a lot more stuff that you're dealing with. Like think about your traditional WordPress app as an example, right? Maybe if I'm running that on VMs, maybe I've got a couple of VMs on a front end that are some kind of load balancer, a couple on the back end that are clustered to, store my database. And so I have a, pretty, rightly sized small WordPress environment on 4 VMs, right? If I decompose that into microservices, now I might have, 8 or 10 or 20, depends on how far I take it, different microservices that I've got out there to support that same application. And that microservice architecture gives me tremendous advantages, right? I can iterate more quickly, I can scale in much more discrete ways. However, it also means there's a lot more things that you have to maintain from a security standpoint that you have to be aware of, you have to alert on, you have to understand what the normal behavior is. So just dealing with the amount of scale is a challenge for a lot of traditional security tools. A lot of traditional security tools also assume a fairly static environment, right? They're assuming that you're going to create a rule that says this source IP to this destination IP over this port, right? They don't really work well in an environment where that source IP might change every day, maybe even every hour. Every time you deploy it, it's going to be different. Or your load balancer is going to move things around, or your Kubernetes may move things around depending on what the load is in the environment. So things that require that sort of static configuration don't really make a lot of sense. And you also have a problem with a lot of traditional security tools in that they expect that entities never die. Like if I deploy a VM, a lot of traditional security tools kind of assume that VM's always going to be there, right? Whereas containers, of course, are going to come, they're going to go, they're going to be ephemeral, and that's by design. You expect that they're going to go away after a period of time. A lot of times, security tools don't handle that very well. They don't show that inventory. They don't really understand how to deal with situations where things are not going to always be persistent. You also have this notion of the responsibility for security shifting left. And when we say shift left, we're talking really about from a development standpoint. If you think about that development life cycle, the far left of that side of that life cycle is the developers themselves. They're building the application, they're packaging that into an image, they're running that image in production. But when we talk about responsibility shifting left, that doesn't mean that the security team or the CISO, their organization is less important or that they go away. But in the traditional world, if I was building an app and I would provide that app to my ops team, they would deploy it, and then they would have some kind of tool that they would probably use to go and assess it for vulnerabilities and configure it for various things. But as a developer, I didn't really have to care that much about that, right? I gave it to them, and some dude that I didn't really know and probably I thought less of because he wasn't a developer anyway, he would actually go out there and he would scan it for vulnerabilities, and he would install updates, he'd SSH into the host and do whatever it is that they do. Well, with containers, that's obviously a lot different, right? But with containers, now it's my responsibility as a developer, right? I need to be able to see those problems early on. I need to be able to fix those problems early on because there is no other guy for the most part, right? What I build is what's going to be run, and if I don't build that stuff securely, then it's not going to run securely. And so the responsibility is a lot more in my plate than it has been historically. And then finally, portability. One of the things that I think customers really love about containers is it gives them a degree of vendor autonomy that really I would say has not really ever existed before. If you think about traditional systems, if you had physical servers before you had virtualization. You know, it was very hard to move off of physical servers, of course, because it just didn't lend itself to that. With virtualization, people kind of got locked into VMware. And then when cloud came along, people sort of got locked into AWS or Azure or whatever it is they may be using. Containers really, for the first time, give you the ability to have like this very modern application, you know, runtime environment, but to be able to do it wherever you want, right? You can have the same stuff that you run on your laptop and in public cloud and private cloud, whatever, and people really like that. Traditional security tools also don't typically handle that well. They kind of assume that you're going to have a particular environment, and within that environment, you're going to have a particular configuration. They often do not deal well with scenarios in which you might have multiple different deployments in different data centers, some public, some private, and so forth. Not to say they can't be made to work with it, but they don't really work very well with it by default. And so those are the things that really make it more challenging when you start thinking about securing containers, because you have these things that kind of make it more difficult for you to do it. But that doesn't mean, though, that containers themselves make security on the whole more difficult, because there's some fundamental characteristics of containers and the way they work that actually give us, from a defender standpoint, some real advantages. Because containers allow us to have a different approach to security that's a lot more automated than what you've been able to do in the past. There's three real characteristics about containers that are very important from a security standpoint that enable you to create security tools like Twistlock that stress automation and scalability and minimize human involvement and that notion of static configuration, because the underlying platform that they're helping to protect based on containers really gives us new capabilities that historically have been difficult to attain. So containers are minimal, right? Like a container as opposed to a virtual machine is going to be doing effectively one thing, right? At least if it's built the right way. You're going to have a container that's doing a kind of a single process entity, if you will. That container, because it's more minimal, it's a lot easier for a security tool to understand what it's doing and whether or not the things that it's doing are normal. Again, going back to that WordPress example that I gave you earlier, if I have a VM that's running WordPress, it's going to have, you know, countless binaries inside of it, right? You know, maybe hundreds of different binaries. And at any given point in time, there might be 50 or 100 different processes that are running inside of that VM, right? Containers, or it's a lot different. There might be a handful of processes. There's a handful of binaries in the image. So I can much more definitively understand whether or not something that's running inside that container is good or bad, normal or abnormal, because the things that I have to compare against are much more discrete. Containers are declarative in nature, which means that instead of me having to go and figure out through some kind of manifest file or, you know, like somebody creating a rule or something, I can look at the container environment, the container daemon, and understand a lot about the characteristics of what it should be doing at runtime. I can also look at the image that you're using to create that container and understand a lot about what it should be doing and, you know, what contents of it are. Because, you know, that container is built from an image, and an image is composed of layers, and layers are described in a Docker file. So I can unpack all that and do that stuff via software that, again, historically has been really difficult to do without having that container ecosystem around. You know, there have always been these attempts in the past for like enabling developers to create some kind of security manifest. Who has ever seen developers actually create security manifests over time? Like nobody ever does that, even though those possibilities have been out there. With containers, because it's not something that's a separate step, but just part of a natural part of the process, it's a lot more likely, in fact, it's just a default thing that'll happen, that you'll actually have those attributes and have that information that you can use. And finally, containers are immutable, predictable. I guess you can kind of argue about the word choice there, but basically, unlike a virtual machine that's kind of unbounded in what it might do over its operational lifetime, with containers, I have a much more clear idea of exactly what it should be doing, right? If I have a container that's supposed to run WordPress and it's supposed to run a particular, you know, SHA-256 of Apache or HTTPD, like that should never change, right? It should never start running Netcat suddenly. It should never start running some other process that's not expected. And because I have those other two characteristics, the fact that they're minimal, so I know what it should be running, it's declarative, I can be pretty confident that my understanding of what it's running is accurate. If I see it doing something that's not part of that list, that's not part of that understood normal behavior, I can make a much more deterministic decision that that thing that it's doing that's abnormal is actually probably malicious, or at least something that should be alerted on. You know, something that if you tie that one data point into other data points, and you know, you can see that not only is it running a process that's unexpected, but it's now listening on a socket that's not normal, and it's writing files to a location that it's not normally writing files to, without you ever having to tell us at Twistlock, these are the rules, this is where it writes to, this is what processes it runs. Simply by observing what's normal, we can detect those attack signatures because we can see these different indicators of threat without you having to tell us what's normal and what those things are that are bad. We just simply know, again, WordPress runs this particular version of Apache, it listens on this port, it's got this MD5, etc. And then we can develop this model that allows us to differentiate between what's normal and what's abnormal. And that's really something that just historically you've not been able to do without containers because the surface area of what you were dealing with was too big and it changed too frequently for you to be able to make those determinations. So the way that we create something that we call a model for every application that you build, the way that we protect your apps at runtime is through a creation of a model that's a combination of both static analysis and actual observed machine learning that we do at runtime. The static analysis part is probably pretty obvious, right? If you have a Docker image, you can look in that Docker image and you can do a lot of things to kind of understand what it should do. Like you might declare ports in the image possibly. You can definitely see what the entry point is to the image. And if you have enough intelligence in the software like we've done, you can actually walk through that in NitScript and figure out like what binaries it's going to run and what the startup sequence is of it and so forth. And so you can kind of develop this skeleton of the model before the image is ever actually started up and run anywhere. So literally the very beginning of the development process, back when you're building your application the first time into an image, we have plugins for tools like Jenkins and other CI processes that allow you to not just show your developers vulnerabilities and fail builds based on the vulnerability posture and compliance posture, but also actually to start creating this runtime model of what we know should be happening when the image actually runs. The really cool part, though, and the part that's really, I think, interesting here, though, is the machine learning aspect of it. It's what do we do next after that? So what we're doing next after the image starts up is we're observing what that container that's running a particular image is doing to create a model that describes what is normal that we will then use throughout the runtime of that image to be able to determine what is normal relative to what the model predicts. So in other words, that model has 4 dimensions. One of them is process activity, like what are the binaries that should run in that? What are the parent-child relationships between those binaries? What are the checksums associated with them? So, if not just saying like, hey, this thing's supposed to run HTTPD, and if a bad guy copies some malware in there and names it the right thing and puts it in the right path, it's still not going to work. It's still not going to be looked at as normal because we know the actual checksum from the origin image and we can compare it at that point in time. Networking is the next thing. So we understand not just the actual like sockets that are listening, but the specific binaries that are bound to those sockets, the specific checksums of the binaries that are bound to those sockets, and also the inter-microservice communications. So not just saying like this one container that's sitting there that's running a particular image listens on this port, but this one container is part of a microservice. It's running in this particular pod. It talks to this other pod or these other services over these particular ports. Here's the direction of the traffic, such that you can actually build up a connectivity mesh that describes the way the application as a whole, all the various microservices that compose it, communicate with one another. And you can learn that automatically without you having to create rules, without you having to go in and like put the application in some sort of learning or audit mode. Just you deploy your app as you normally would with the same tools that you normally would without any changes to the images or the config files that you use to do so. We learn that dynamically, create that mesh, and then allow you to actually enforce that. So if we know that the front-end microservice talks to the back-end microservice over 3306 and it's a particular direction of communication, we can actually actively drop traffic that does not fit that pattern without you having to go in there and create a rule and tell us that the front end talks to the back end over this particular port. We see that, we learn that, we add that to the model, and thus we're able to protect that and actually drop traffic that's not compliant with the model without you having to do any work to tell us how to inform it. The third part is file system activity. So like what are the files that are, the file paths that are being read from, that are being written to? What are the types of files that are being written someplace? Like if your app normally is writing, text files to a particular path and suddenly it drops a binary there, that's probably indicative of some sort of problem, right? The fourth one is system calls. We can understand the system calls that a given application is making. We can create basically a model that enables us to see if there's attempts to run system calls that are not allowed by that and be able to see that anomalous activity. And so that 4-dimensional model, again, process, file system, network, system call, allow us to then compare throughout the time that the containers are running what they are actually doing at runtime relative to what the model predicted. So as opposed to that old world model of security where I had to have a blacklist that said this thing is bad and this port is okay and this other port is bad, What we're actually saying is we know only the things that are allowed, the things that are normal, that are the proper actions that should be occurring within the containers, and thus anything outside of what's predicted is automatically seen as anomalous. And then you can prevent it, you can stop the container, you can alert on it, whatever you would do from a normal security response standpoint. But the key thing is the automation. At no point do you have to inform the tool that this is what's good or this is what's allowed. You learn that just through observing the applications that are running, observing the origin images that are used to run the applications. And that gets you into this new world security model in which the modeling is integrated into the deployment process. You're starting to create that model from the very beginning of the CI process. Every application you have effectively has a custom tailored policy just for it. Every time you do a new build, you get a new model associated with the particular build that you're talking about, literally correlating the models to the digest IDs of each image. So every time you do a new build, you get a model that's calculated specifically for that build. And because it's built for that particular image, not for the infrastructure, it runs anywhere that you want it to. You don't have to be dependent upon running in a particular data center. You don't have to be dependent upon the particular cloud service provider you're having. The security basically follows the app because it's a very app-centric approach to doing the security. And that allows you, as you can imagine, when you see the typical kill chain pattern, to be able to stop it in various checkpoints. Like we have the system call sensors, network sensors, et cetera. Again, all of which are informed through this autonomous machine learning approach that we have. And that basically is the summary of it. If there's any questions, I'd be happy to take them. If not, I'll turn it back to Tricia. Yes. Okay.
All right. One thing is when you, depending on the environment, the system might need to connect to external systems. How do you react on this? Let's say you're in CI environment, maybe all your systems are mocked. Internally, you don't need to do anything, but in real world, actually, you have to connect that one. And the follow-up is how do you do with denial of service, which might come externally. They look like a normal activity. Is there any learning about it?
Yeah, good question. So in terms of the environment, the model is designed to be independent of the environment. If you're connecting to external services, that's okay. That's not something that we're going to look at as being anomalous just because you ran one thing in dev and you're connecting to different services in production, as an example. The question about denial of service, one of the attributes that you'll see with denial of service is just an extreme amount of inbound connection events. And you can look at that as anomalous because that's outside of what's expected. You can block on that or alert on that. But by and large, this is really more focused on sort of active threat detection scenarios, more so than like DDoS scenarios, which are really better handled by like an ingress firewall or ingress sort of routing policy instead. All right. Thank you.
Thank you, John. I'm sure John will be available afterwards for any additional questions, and you can also visit the Twistlock booth on the show floor. Our next speaker, I'd like to introduce Zach Butcher. He's going to be doing his session on building robust services with GRPC.
Cool, thanks. Alrighty, hey, I'm Zach Butcher. I'm an engineer at Google. I actually work on not gRPC directly, but an open source project called Istio, which uses gRPC pretty heavily. And Istio is all about networking microservices, and so we deal quite a bit with how we do microservices robustly. So first off, what is gRPC? Really, it boils down to a set of server implementations that talk this protocol in a couple different languages, and you provide an interface declaration that says, this is the service that I want to expose. Typically, that comes in a protobuf, but you can actually use different things like Swagger and that kind of thing. Run it through the protocompiler, and what you get out are idiomatic client and server interfaces that you can use in a variety of different languages. So the example that we're going to kind of walk through in a bunch of different scenarios today is a health checking service in gRPC. So gRPC has a ton of different features built in. This is a small subset. And things like being able to propagate metadata, context, and deadlines throughout your services. Interceptors to handle cross-cutting concerns. It has support for streaming APIs, both one-way and bidirectional. So you can, clients can send multiple requests for one server response. the server can send multiple responses to one client request, and you can have clients and servers that do multiple reads and writes in the context of a single request session. gRPC does things like client-side load balancing, which is really, really cool, very powerful. It has flow control and support for authentication in a couple different ways. And today in this talk, we're really going to dive into kind of these 4 or 5 areas, really. So first off, deadlines. This is all my examples today are going to be in Go, so I hope that's familiar for people. This is a pretty normal Go call. Normally, when you make a Go call, you add a deadline to a context, and then you send that context down. And that has a couple of different effects. First off, we're guaranteed that this call is going to return in my client application after no longer than 5 seconds. Returns earlier if the server returns early, obviously, but otherwise we'll get an error and we can respond to it. But this means we're not going to tie up resources waiting around. I don't know if people have had to debug scenarios where you make calls and they never come back and your server hangs, and you get more requests to come in and you make more calls out and it just hangs and you lose resources, and it can be kind of annoying to go debug. And so this is very simple. And what's nice is that this gets propagated to the server as well. So the server can use this information to make decisions, right? You can do things like say, hey, this deadline is so short that I actually can't do meaningful work. So I should just, return an error immediately. Or you can take, and the server, and this is a pattern in gRPC that you should follow, is you can propagate these contexts down. So when a request comes in with context and metadata, I can turn around and propagate that to the other services that I call downstream as a result. And what this means is that every service in the call graph can choose to cancel work and stop when it no longer cares, right? Because the client is unblocked immediately after 5 seconds. It doesn't matter if your service responds or not. Nobody is going to be listening for it. And that's actually one of the reasons that gRPC uses deadlines and not timeouts. A deadline is a point in time at which the work no longer matters. A timeout is some relative thing that I have to compute based on the current time, which could be different on different servers. Deadlines are a lot simpler in that respect, right? There's a drop dead time that everybody can agree on. gRPC also supports this general metadata propagation. So one example where this is really nice is request tracing. I want to, understand the flow of requests through my system as a result of some client call. Tracing is awesome to do that. And so you can use gRPC's built-in metadata to handle propagating that trace information for you. And of course, deadlines are actually just a special case of general metadata propagation. Interceptors are maybe the single most powerful feature as far as building services that behave well in production and that have desirable characteristics. They're really, really powerful. So in this example, and generally just any cross-cutting concern, anything that I want to happen for every client, for every client call made with this client, or every request received by the server, go reach for an interceptor. So this example, you can plug in Prometheus interceptors and get Prometheus stats generated for you automatically for every request, every request that your client sends, every request your server receives. And I just want to point out all the examples that I'm giving are client side, but essentially everything exists for the server side in a mirrored way. But what's really, really powerful is using interceptors together with gRPC's ability to propagate metadata. So together we can do things like automatically propagate trace metadata for every request without any code at any call sites, without any code. We do a little bit of wiring up when we create a connection, and we get tracing flows through the system. And you actually don't even have to do work to use that data in your service to get benefit out of it. If you come back later and you say, I actually want to add more rich information to my trace, I want to more deeply understand some of the business logic that's happening in my server, the information is in hand in the context for you to go annotate your application with that in place already because you use interceptors to propagate it through your system. Really, really, really powerful. You can also do things like automatic deadlines. So we talked about deadlines, and I showed you a deadline at a call site. That's not great, because that means that every single call site, I need to make sure that I wire up the deadline. And that means I need to, if I want some consistent deadline for for one service, I'm calling my auth service, and I want the deadline to always be 5 seconds when I call my auth service. I have to handle every call site that happens, going and wiring that up. That's no good. You can actually do things like use interceptors to set deadlines and do retries and other pretty sophisticated things, which we'll get into more. Client-side load balancing is an incredibly powerful feature. It really lets you do a lot of really impressive things, and it lets you build a system that responds well to the normal failures of distributed systems, because your clients can intelligently react to things like hosts that fail. So load balancing in gRPC is a little bit different than typical request load balancing. If you think about a typical REST-based service, I have a client and I establish a connection to a server, and that probably hits a load balancer that decides what backend that goes to, and then I make my request. And hopefully we don't tear down that transport, because transport connections are expensive to build, so I would like to be able to reuse that. gRPC does not. It actually stands up long-lived connections. And so in gRPC, when I go and dial a service, that's actually exactly what happens. So you can describe a whole set of backends for gRPC to dial, and a gRPC server will start up and it'll go make connections to some subset of those backends. And gRPC will handle it will handle load balancing according to whatever strategy you provide it across those backends. And it has features built in like lame ducking. If the server stops responding to me, then I'm not going to send requests to it. I can take it out of rotation, and I can load balance across the servers that are giving me good responses back. And it can do things like automatically bring that server back into rotation after we wait, kind of circuit breaking style behavior where we bring the server back into rotation slowly. So in this particular example, we can hook up a name resolver that uses Kubernetes API server to resolve hosts, and this client will automatically round robin across all of the pods that expose, the service, the health check service that we're dialing. That's really, really powerful. And in scenarios where probably the most common use case for gRPC is in kind of a same trust environment. So I'm in my Kubernetes cluster, for example, where I have a reasonable assurance that clients are going to be well behaved. It's not the example of an outside user calling my server. There, I don't know that my client will be well behaved or not. But in a reasonable environment where I can, where we trust the client, you can actually pull middle load balancers out, and you can avoid extra network hops, extra latency, extra points of failure in your system by having the client do load balancing and avoiding these middle load balancers. This is used extensively at Google. Retry strategies. How many people have written a for loop around an RPC call? Never do that. It's awful. It's super easy to get it wrong. You don't, do you have back off? Are you randomizing your weights so that you don't have stampeding? How are you doing the back off? What are, all this stuff, really annoying, finicky code to write. Nobody should ever have to write it. It should be written one time. And so there's libraries that you can use to set up retries, at individual call sites, but also via interceptors, right? So I can say any call made with this client should use a linear backoff that waits a certain number of times, and and only retry under these scenarios. You can get very sophisticated with the kinds of things that you retry and the strategies for retrying. And this is, again, incredibly powerful. You don't never write a for loop around an RPC call again unless you're writing a read, modify, write API. Use libraries to handle retries for you because it's just so much easier. People write it wrong all the time. And I do want to point out, by the way, that a lot of these examples that I've been showing here are actually not built into gRPC directly. Just about everything that I've shown you are libraries that I pulled in from third-party systems, the GRPC ecosystem and stuff. One of the core principles of gRPC is extensibility at every layer of the stack. And so it provides API hooks to be able to implement functionality that you need, right? So we talked about load balancing. You can implement name resolvers in a variety of places. You can implement different load balancing strategies. You can do sophisticated things like have an interceptor that communicates load information in the metadata. And you can write a load balancing plugin that uses information that gets propagated to make intelligent load balancing decisions for you. gRPC actually does some of this itself, and it uses interceptors and the libraries that it provides for you to use. It uses internally to do those kinds of things. So gRPC's flow control is implemented like that. Very, very powerful. gRPC also provides hooks for a variety of authentication, both transport level and per request. So you can do things like transport level encryption with TLS, both client and server side. So you can perform mutual TLS so that I know who I'm being called by and who I'm calling with assurance. You can also do things like handle attaching OAuth tokens or JOT tokens to every request. And you can hook those up programmatically so that libraries can handle going and refreshing your tokens for you, and they're attached to your request via an interceptor as the request goes out. So that at my call site, I don't need to worry about the plumbing to go get the credentials. I can be assured that the call that I make with this client will have the credentials that I need to call the client without muddying up code. Really, really nice. And I do want to make a quick note that everything that I've shown here so far is language specific. So gRPC supports a lot of languages. There are 9 officially supported gRPC implementations. There's a whole slew of open source and all those are open source. There's a whole slew of other non-officially supported implementations as well in a variety of languages. But the libraries to do everything differ per language. One of the examples that I gave you was an interceptor that generates Prometheus metrics for you. Awesome, really, really useful. It's really nice. As far as I'm aware, it only exists in Go and Java. So if you're writing Python servers or C++ servers, you're kind of out of luck. You have to go either implement that yourself, which is it's not that hard, but it's work that you have to do that you shouldn't have to go do. And so that's kind of challenging. So that is kind of one of the downsides. And there's also kind of a lack of centralized control. That retry policy that we showed, if I have to go change that, that's actually a real big pain because we had hard-coded numbers in our binary, right? The speaker before me, we talked about the process from development to operations and that flow. The farther back you have to go in that flow to make a change, the more work and the more risk is associated with deploying it out into production. It's really, really awesome to be able to do things like control retries with configuration at runtime rather than numbers hard-coded into my binary. And so there are tools and libraries that exist that you can use to build out that kind of functionality, things like configuration-driven retries. The primitives exist to do that, but today there don't exist implementations to do that. So I just want to call out that a lot of these resiliency features, a lot of these features that help build robust services, are also available in the form of service meshes, which is kind of a newer topic, but effectively they're language agnostic ways of abstracting away the network from your application. Because that's really a lot of what we've gotten into. A lot of these features that gRPC provides help you abstract away the network. And so service meshes do the same. But the advantage is they typically tend to be language agnostic, and they provide mechanisms for centralized control. And of course, I work on Istio, so I would be remiss if I didn't mention it, but there are plenty of other, Linkerd and Envoy are both in the CNCF and are really great service mesh implementations you should go check out. Istio is as well. And all of gRPC is an open source project. So go check it out. It's on GitHub. The website, grpc.io, is there. Go join IRC. Tweet at us. Send emails. And people will respond. If you have questions, people will answer very quickly and all. At this point, does anybody have questions? And I threw a ton of information real fast. We flipped through code. But any questions that people want to answer? Hey, yeah. Oh, just timeouts can be hard because I have to because a timeout says 2 seconds from now this request is no longer valid, right? So that's what gRPC does. gRPC propagates a specific time, right? So I don't need to do math at call sites to determine how much more budget is on this request, right? I'm not having to subtract numbers to say there's 2 seconds left. I can just propagate one piece of data. Here's a time, and I don't have to modify it as it flows through the system, right? So it's more simple in that sense. Sure, yes. Yeah, I mean, that is effectively yes. That's what you want. But just, some RPC frameworks use timeouts as their style of doing things. It's just it turns out in the implementation, it's a little bit simpler if you use deadlines. The absolute times rather than relative tickers that you have to keep track of. Cool, any other questions or anything? Hey. Mm-hmm. So those baseline features are all going to be there. So support for deadlines is one of those core features that is important enough to always be there. Some of the things that aren't always there are some of the lower level, like network flow control code differs between implementations. So some have substantially better performance than others. There's a lot of the library parity is not the same between languages. In particular, Java, C++, and Go tend to be first-class citizens, and a lot of the other languages tend to have less featureful libraries. Cool. Hey, one more. Yeah. So if we run in Kubernetes, why do we need a resolver? Because gRPC does load balancing differently than typical applications. It load balances per request across long-lived connections that it opens. So it's not going to ask the kube DNS server, hey, which host should I call for this request, opening up a connection and then sending it. It's actually opening up a set of transport layer connections and then multiplexing across them, right? So the load balancing is in the application and it's not happening at the network layer. It still will because gRPC will go and ask multiple times, but you're not guaranteed to get kind of the same. We can talk at length about kind of some of the differences because there's some subtle things that happens, but in general, you're not gonna see like poor load balancing performance because you're not using a Kubernetes name resolver. You can get reasonable performance out of just deploying gRPC into Kubernetes and relying on Kubernetes load balancing functionality. But you can get better performance and better load balancing characteristics and more sophisticated load balancing schemes doing it in the server itself. In the client, sorry, yeah, in the web server, in the client making the call, sure, yes. Alrighty, cool, thank you.